I'll wait for that to come up. Basically, what I'm going to be talking about today is thermophysically and morphologically distinct set of craters, or more particularly the crater Ejecta on the moon that we've mostly identified using diviner radiometer data. I'd like to acknowledge my co-authors, which will come up in a second, Eugenie Song, Paul Hain, Ashman Basavada, Becky Gent, and Dave Page. And I'll show and talk more about this image later. Just put up a pretty picture for the intro side. I'm not quite sure how to move on. Yeah.
Is this PDF?
It's a PDF.
Okay, you're going to have to say next.
Next.
Or not. Well, we don't. Any questions?
Oh boy.
Try the active one.
Point in this direction.
Nope.
Okay, you'll have it.
All right. I'm just going to say next slide throughout the talk. Thanks. This is a piece of an L-rock black mosaic. It's near about 150 east, about 4 south, and at the center you see a relatively fresh crater. You can see the bright ejecta around it. Rock abundance data, which I'm not showing, shows high rock abundance within the crater itself. It's about 1.5 kilometers across. There's nothing terribly unique about it, at least in the WAC mosaic. If you go to the next slide. All right. All right. If you go to the next slide, this is the diviner nighttime regolith temperature map, and you'll notice that you've got this very large region of relatively cool temperatures around it. This is qualitative because I'm mixing a whole bunch of different night times, and they're normalized so that you don't see striping with one another. But this 1.5 kilometer crater has this region of 50 to 100 kilometer diameter, even larger region, extended region of cool surfaces in the nighttime data. And that basically indicates at a qualitative level, which I'll talk about more later, basically unique thermophysical properties in the upper couple centimeters of the surface. Next slide, please. All right, and if we take a look at the larger, basically across the moon, we see these things in a lot of areas. Everywhere where I have an arrow here in this just random highlands shot is where we see one of these features. They're quite common. And if we go to the next slide, we've counted about 435 of these occurrences between plus and minus 50 degrees latitude. It doesn't necessarily mean that they don't occur at higher latitudes. It just gets harder to identify at higher latitudes because of the influence of topography on the nighttime temperatures. They're associated with craters about 0.1 to 1.5 kilometers in diameter, maybe even smaller. We're at the limit of our resolution with the diviner data. All of these things are fresh craters based on both elevated rock abundance associated with the crater itself and a relatively high albedo. But more importantly, not all fresh craters have these types of unique thermophysical properties, as well as morphological properties, which I'll talk about in a minute. The ejecta and cold spot radial patterns, basically the radial symmetry or asymmetry is variable, indicating that we have a variety of impact angles. And each one of these little white dots represents one of these occurrences, and you could probably try to find some kind of regional correlation if you really wanted to, but to first cut, there isn't one. Next slide. We're going to focus on 24 of these prominent equatorial cold spots. We've identified them for a more detailed investigation at the equator, mostly just because the nighttime temperatures will be relatively similar to one another. Next slide. All right, back to this one, the nighttime regolith temperature map. Once again, normalized. We're going to look at the L-rock NAC images, basically put together a mosaic shown by the white box here. Next slide. All right, so this is that mosaic of 4 NAC images. You've got the scale bar here. It's about 1.5 kilometer diameter crater. This is one of the largest ones that we do see on the planet. There's some, what I think are unique morphological properties. First thing that you notice is that we've got this sort of continuous, progressively lighter toned layered ejecta within about 5 to 10 crater radii. And as you go from here to here to here to here, we see discrete layers with discrete edges, and they get progressively lighter toned. The layers themselves, and I'll show a higher resolution image in a minute, have sinuous striations, they have abrupt terminations, and are diverted by topographic obstacles such as rocks. And so one thing that this is highly suggestive of is fluidized flow, and I mean that in the most generic sense of the term. I don't want to get into taxonomy arguments here, but this is flowing across the surface rather than the stuff being in place ballistically. Next slide. Looking at this more closely, you can see we've got these sort of dark shadows. At the heads of each one of these dark shadows is a boulder on the surface. So the boulder is basically protecting the area behind it from the deposition of the material as it's flowing across the surface. Once again, you can see the sort of the striations in these layers. Next slide. Looking at a little bit closer and a little bit farther away, notice that one thing I should point out is these have low angles of solar incidence to bring out albedo markings. At higher angles of solar incidence, you can see sort of more of the shape of the surface. You can see the abrupt terminations of these different flow lobes. You can see some of the layering. The source crater is up there about a kilometer or 2 away. Next slide. So, oh, and yeah, this is at a higher angle of solar incidence, and you can see that these flow lobes, some of them at least, which have significant thickness to them. Next slide. As we get farther away, this is within an area of the unique thermophysical properties. This is 13 kilometers away from the crater, and the patterns that we see on the surface become more diffuse. The source crater is off to the upper right here. You can see basically where we've got these sort of topographic obstacles, you can see streamers or trailing features behind them, indicating, once again, I'll be suggestive and say that basically the topographic obstacles inhibited flow and created some turbulence behind the object. And as we get farther and farther away, these features persist but get more and more diffuse, even though the thermophysical properties themselves are quite strong. Next slide. Okay, so back to the thermal modeling and the thermal data. We can put together diurnal temperature curves, and here in the top we've got surface temperature versus time, and the time is kind of this unique hours after noon. Basically, we've got sunset on the left, sunrise on the right, midnight's right in the middle, and the average regolith temperature, which doesn't show a lot of distinguishing features across the planet or across the moon, shown in red, and you can see that the average cold spots follow this temperature curve, but remain about 5 to 10 degrees Kelvin cooler than the typical regolith. And some preliminary modeling, basically much of the moon can be simulated using a sort of a fluffy layer of a couple centimeters on top of a more densely packed layer underneath it. And the modeling that we've done to try to account for this temperature difference indicates that we've got a contrast in the thermophysical properties in the upper few centimeters relative to the surrounding terrain. And it's not quite unique, but it's a thicker fluffy layer or an even fluffier layer. But regardless, we've got these very large areas where we've affected the upper couple centimeters of the surface. And in addition, I'm not going to get into this too much because this would be kind of a messy talk of its own, but the daytime multispectral data also indicates that cold spots are slightly rougher than the surrounding terrain, which is sort of consistent with, say, a fluffier surface. Next slide, please. We can look at some of the scaling relationships, and this thing, basically if we take the unique thermophysical properties as being related to that crater, the cold spots cover huge areas relative to the parent crater. And if it violates some basic scaling relationships of ejected thickness, volume, etc., assuming ballistic emplacement, we took the upper few centimeters of that entire cold spot area and tried to shove it back into the hole of that crater, it's too much volume. It wouldn't fit. In this slide here, in the chart here, we've got crater radius on the bottom. We've got maximum runout distance on the vertical axis, and you can do a regression. Next slide. And by looking at these relationships, this is taken from Pete Schultz's 1992 paper. You can at least suggest some things about the style of emplacement, especially based on the exponent in the regression. A positive exponent indicates we have turbulent flow. If the exponent is close to 0, it's consistent with ballistic emplacement. And if it's negative, such as in where we have a thick atmosphere, such as what we see on Venus, it would give us a negative exponent. Okay, next slide, please.
2 minutes, Joe.
Sure. So, do we have fluidized flows here? A couple things. Large areal coverage and thickness of the deposit preclude simple deposition of ejecta. We don't see any spectral or albedo signature in the Wacker Clementine data, despite this thermophysically modified surface. So that indicates that we have limited deposition and/or stripping of materials throughout these cold spot regions. In closer to the crater, we see lots of indications of ground-hugging flow morphologies and high-resolution images, and the crater runout scaling relationships are consistent with a turbulent flow. Next slide, please. So the hypothesis we're going to put forward here, which it's labeled hypothesis, not conclusion, is that cold spots mark the locations of recent cometary impacts. What I've been alluding to is that we need to find a source of, say, gas to produce a fluidized flow and can modify the surface without necessarily depositing material. You can sort of back it up in a harm-waving fashion that, at least several percent of the volatiles will remain gravitationally bound in a cometary impact. It'll provide the volumes necessary to affect the large areas without depositing new material. But one of the questions we have is really what's the effect of this highly energetic expanding gases impacting or flowing across a particulate surface in a vacuum? And is this the means of, say, fluffing up the existing regolith or somehow modifying it in that fashion? Next slide. There are some alternatives, and I'm not going to get into them too much. I don't really think that they provide a very good explanation for what we're seeing. You can raise maybe ballistic sedimentation, where we have basically ejecta flying out, hitting the surface, kicking up more stuff, and cascading. You have a cascading effect, but that requires relatively large impacts. And why would this only occur with some fresh craters? I guess I'm going to the... Okay. Dry fluidized flows, so can we just have particle-particle collisions? But that would result in deposition of new material, and it would require very large densities of material, concentrations of solid material flowing. And a couple other things you can invoke, maybe volatile rich asteroids or whatnot. Next slide. All right, so to conclude, I think sort of regardless of the specific mechanism, I think we're seeing evidence for fluidized flow features which are common on the moon and should be likely to be identified on other airless body surfaces, at least with significant gravity. Our best guess is this volatile rich impactor is responsible for this. And it raises a number of questions such as, could this be used to estimate comet-asteroid flux ratios, or is this a means for understanding emplacement of water on the moon? So much, much more work to be done, and I'll leave it at that. Thanks.
Wow, we've got no time for questions, but we'll take 2 at the front, and that's it. Where's the coming around the back? Oh, you just have to shout out because we don't have the time, so.
On slide 11, embedded in the, embedded in the fluidized flow pattern, there were a couple of cases of chains of indentations that looked to me like the saltation of a 10 or 20 meter boulder energized and moved by the flow. It would also seem that one could derive some physics of that flow, the nature of the material, velocity, viscosity, etc., from that.
What I didn't say with that slide was that particular image was on a larger slope, basically the wall of a much larger crater in the region, where boulders are basically mass wasting down the surface. And I honestly can't tell if that's related to a later event or if that was related to the crater itself.
And Bill, this is going to count towards your talk, so
Oh. Oh, just very quick, just a quick comment. Comets, as far as we can tell, don't seem to be a big part of the lunar impact flux today. So I don't know if the comet hypothesis works, but the question I had is, what fraction of all the stuff, of all the small impactors you're looking at, have these properties?
I don't know, a significant but not majority. That's as best as I could say right now.
Okay.
Yeah.
All right.